Okay, good morning to all. In the last class, we discussed group, subgroup, and normal subgroup. And today we introduce a coset. So, what do you mean by coset? Suppose if we take some group, so let G be a group. So, we are going to define what is coset. Suppose let H be a subgroup of G. Let H be a subgroup of a group G. So, whenever I use G, G means group with some operation. Okay? Now, if we take some element A in G, then the set A times H. That means what? You have to multiply A to the each element of H. That is, the elements of AH is of the form A times small h such that H varies in capital H. So this is called left coset. So since the element in the left side, therefore it's left coset. Similarly, we define the right coset HA equal to H times A, where H varies in H. Okay, so this is the left coset, and this is right coset. Okay, now, so if we take two right coset, suppose if we take one right coset, so we collect all the right coset or left coset, we denote the set is G by H. That is called the quotient space. So anyway, so this is a collection of all either right coset or left coset. Better we take a right coset or left coset. So set of all AH such that now here A is varying. For each A, we have right coset or left coset. So we are varying the element A in H, sorry, A in G. Now this is set. Now we are going to impose some operation on the set G by H to become this G by H, become a group. That a group is called a quotient group. So that means if we take two coset AH and BH, suppose you are multiplying AH into BH, what we are expecting that again should be a left coset. So we are expecting AB times H. So this is true only when H is normal subgroup. So if and only if H is normal. So product of two right coset is again is a right coset if and only if H is a normal subgroup. Otherwise, product of two right coset or product of two left coset may not be a right coset or left coset. Okay, so therefore H is a normal subgroup. If H is a normal subgroup, then product of two right coset is actually right. Now, this is an operation. Okay, maybe you can take some usual multiplication. Now, with respect to this operation, the set G by H with respect to this dot multiplication, coset multiplication, form a group. So this is a form a group only when H is a normal subgroup. Okay, so this group is called a quotient group. Quotient group, or sometimes called factor group. Factor group. Okay. So given any group, given any normal subgroup, we can create a new group, that is the quotient group G by H. Okay. Now, for example, if it so before going to that, we define isomorphism, all the things. Okay. Now we define what is homomorphism between two groups. Homomorphism. Suppose we have two groups. We call G1, comma some star. It's one group, and G2 is another group. Because some other operation, maybe we call some delta, or you can take some other any operation or composition, that is your wish. Anyway, we take two different groups. Maybe we take some O R groups. So a function from G1 to G2 we call F is a function from one set G1 to G2 is said to be homomorphism. Said to be homomorphism, what is a group homomorphism? Because We are defining function between groups, therefore it's called the group homomorphism. Group homomorphism if is preserve the operation, that is f of, if we take any two elements g1, suppose we take a, but in between a and b we have operation stop, so this is equal to f of a, but here f of a is in g2, but g2 operation is o, so f of a o or circle f of a. So if the function f preserves the operation for any element a comma b in the domain g1, then we say it's a homomorphism. So for example, if we take the integers, so we take g1 is set of all integers with respect to addition. Even you can take the g2 also set of all integers with respect to addition. Now we define a function f from z to z defined by f of n equal to, suppose I am defining 2 times n for all n. Now we have to prove that this function is a homomorphism. So if you take any two elements n comma n, then what is f of n plus m? So by the definition, this is 2 times n plus m. And if you multiply 2 inside, we get 2n plus 2m. But f of 2n is nothing but f of n plus 2m is nothing but f of n. Since domain and codomain are same operation plus, therefore for any mn is satisfied this. Therefore this f is a homomorphism. Okay. So this f should be homomorphism. F is a homomorphism between z and z. Okay, this is the first example. Suppose if we take, I am taking G1 is set of all n by n invertible matrices. So G ln of R is nothing but set of all n by n matrices whose determinant is non-zero. So this is a group with respect to matrix multiplication. Suppose if we take another group, I am taking that if we take R star, R star means R different singletons. You are removing 0. That is we call R star. So real number, non-zero real number, and this is a group with respect to multiplication. Now we define a function from the G1 to G2 by, so f of, if you take any matrix A, so I am going to define determinant of the matrix, because determinant is a real number. Okay. Now we have to check that this function is a homomorphism or not. So if we take any two matrices, we have to find what is f of AB. So by the definition, f of AB is nothing but determinant of AB. By the properties of determinant, this is equal to determinant of A into determinant of B. But determinant of A is nothing but f of A into determinant of B is nothing but f of B. So this multiplication is a real number multiplication. This multiplication is a matrix multiplication between A and B. Okay. So it's preserve the operation for any matrix AB. Therefore, this f is a homomorphism. So this f is a homomorphism. There are so many homomorphisms are there. So for example, if we take one more example, suppose I am taking G1 is set of all matrices, all n by n matrices, and I'm taking, this is a group with respect to matrix addition. If we take the another group G2, I'm taking set of all real numbers. So this is a group with respect to addition. Now define a function G from G1 to G2. So defined by G of, if we take any matrix A, I'm going to just define the trace of the matrix A, because trace of the matrix is also a real number. Now we have to check that this is a homomorphism now. But here we have to take any two matrices, because here addition is the operation, therefore we have to take A plus B. By the definition of G of A plus B is nothing but trace of A plus B. But by the properties of trace, it's nothing but trace of A plus trace of B. And trace of A is nothing but G of A, and trace of B is nothing but G of B. So therefore, this G also preserves the operation. Okay. So therefore, this G also homomorphism. Okay. Therefore, this G is a homomorphism. Now, when we say a homomorphism is said to be isomorphism, the function both to 1, 1 and on 2. So already we know the definition of 1, 1 on 2. So now, what is the definition of isomorphism? So when we say a homomorphism or a function is said to be isomorphism. Okay. So definition, that should be a homomorphism. Okay. A homomorphism, maybe we call some name or F from some group G1 on to G2. Otherwise, if you write G1 to G2, if so, when we say a homomorphism is said to be isomorphism, if F is bijective. So bijective means what? Both 1, 1 and R2. So otherwise, just F is bijective. If F is bijective and then homomorphism, then we say is a isomorphism between two groups. So if suppose there is a isomorphism between G1 and G2, we denote this notation. G1 is isomorphic to G2. So this is nothing but isomorphic. G1 isomorphic to G2, the function F is called isomorphism. Isomorphism means what? It should be homomorphism and bijective. Okay. Now we discuss the example of isomorphism. So if you take the same example, suppose if we take G equal to set of all n by n matrices over R and take G2, another group G2.
Check whether it is homomorphism also, sir.
Yeah. If it is given that homomorphism, no need to check homomorphism. But if it is not given, you have to check first homomorphism and then you have to check this bijective or not.
Bijective.
So, okay. Now the another group I am taking the real number. So now suppose they will not give the operation. What is the operation? But we know that clearly set of all n by n matrices is a group with respect to addition, matrix addition. You should know what is the operation. That's it. So clearly set of all matrices is not a group with respect to matrix multiplication. But if you take set of all invertible matrix, that form a group with respect to multiplication but not addition. So therefore, given any set, they directly say it's a group. Sometimes they will not mention the operation, but you should know what is the operation of the set. Okay. So clearly this is also a group with respect to matrix addition. This real number also a group with respect to addition. Suppose I am defining the trace function. So we define F from G1 to G2 defined by trace. G1 to G2 defined by F of A, we are assigning trace of the matrix. Now already we proved that this F is homomorphism, right? So therefore F is homomorphism is clear. Now we have to check this is 1, 1 or not. So 1, 1 means what? A different element should be maps to different element. Is this 1, 1? That means what? Different matrices have always different trace? Need not be. Why? Because suppose I am taking some matrix A, if we better case 2 by 2 matrix. Okay. Suppose I am taking 1, 0, 0, 2. Suppose I am taking this matrix. So what is the trace of this matrix? Is 3. Now we take another matrix B. We take 3, 0, 0, 0. This is also a 2-bit matrix. But what is the trace of this matrix? Is also 3. So therefore we have different matrix but the same image. Therefore this function is not 1. So F is not 1 to 1. Now we have to check this function is on to or not. So on to means what? If you take any element in the range in the codomain, at least one element maps to that element. Okay. if you take any element, suppose I am picking some arbitrary element A in the codomain, but codomain is a real number, therefore I take let A belongs to R. You have to prove the function is onto or not. If you take any element in the codomain, suppose I take arbitrary element A in R, can we find a matrix A, capital A, such that the trace of the matrix should be A? Yeah, you can always find. So we can find or choose the matrix A. Simply we can take A0 on the diagonal. We can take any other one. Anyway, because we are going to find the only trace. So I can choose this matrix from the domain such that what is f of A? F of A is nothing but trace of A. What is the trace? A plus 0 is nothing but E. Therefore, I can find the matrix A. The image is this. Therefore, if we take any element in the codomain, we can always find the pre-image. Therefore, this function is onto function. F is onto. But F is not 1, 1. Already we proved that F is not 1, 1. Therefore, this F is not isomorphism. Because it is a homomorphism and onto, but its failures 1, 1 condition. Therefore, this function is not isomorphism. Okay. Even if we take the determinant, in the previous example, we defined the determinant. This also already we know that this is a homomorphism. Now we have to check this is a 1, 1 or not. Is this 1, 1? That means what? The different element, different matrix have always different determinant? No. Why? Because take this one. I take 1, 2, I'm taking some 3, I'm taking 0 here. So this is upper triangular matrix. Therefore, what is the determinant of this? Is that just a product of the diagonals is nothing but 2. Suppose I'm taking another matrix B, I'm taking suppose 2, 5, 0, 1. So this is a different matrix. Again, what is the determinant of this? Is again the product of the diagonals 2. So A and B are different, but the images are same. Therefore, this function is not 1, 1. So F is not 1, 1. Now what about onto? Is this onto? That means what? If you take any element in the codomain, but what is the codomain? Non-zero real number. If you take any non-zero real number, we can always find a matrix whose determinant is that non-zero number. Suppose I am taking A in R star in the codomain. So A is R star means what? A should be non-zero number. So we can find a matrix A whose determinant is A. So what is that? If you take a simple case 2 by 2 matrix. So what is that? A 1 0, you can take anything here, some 0 in one, no problem, you can take 0. Now this is a diagonal matrix. Now what is the determinant of A? This is a product of the diagonals, therefore A into 1 is A. Therefore F of A is nothing but determinant of A. Here determinant is A. Therefore given any non-zero element, we can find a matrix. Therefore F is onto. F is onto, F is homomorphism, but yet F is not 1, 1. Therefore this F is not isomorphism. Okay. Okay. So we have to find some isomorphism. So what is the example for isomorphism between two groups? Another example. Suppose if we define F from Z to Z defined by F of n equal to minus n. That number maps to negative of that number. So we can easily show that this is a homomorphism. Why? Because if you take F of, take any two elements, n1 plus n2, it should be equal to, by the definition, minus of n1 plus n2. If you multiply minus inside, we get minus n1 minus n2. So this is minus n1 is nothing but f of n1 plus minus n2 is nothing but f of n2. Therefore, f is homomorphism. Now we have to check 1, 1 function. So 1, 1, suppose there are equivalent definitions. Suppose what is the definition of 1, 1? Suppose f of x equal to f of y. If you take f of x equal to f, what we have to prove? We have to prove x equal to y. Or suppose you assume that x not equal to y, we have to prove that f of x not equal to f of. So suppose assume that f of x is equal to f of y. Suppose the image of two elements are equal. Now we have to prove that the element should be equal. So by the definition of f of x is nothing but minus x. By the definition of f of y is nothing but minus y. Now multiply minus both sides, we get x equal to 1. So whenever f of x equal to f of y, we get x equal to y. Therefore, f is 1, 1. Now we have to prove that f is onto. So onto means what? Given any element in the codomain, we can always find a pre-image. So we can choose some arbitrary element em. So we take element in codomain. So we have to find a element in the domain. So we can choose minus m. So therefore, f of minus m by the definition is minus of minus m. So by minus of minus m, therefore we pick this m in the codomain, we can find a minus m in the domain which maps to this one. Therefore, f is on. So f is both 1, 1 onto and homomorphism. Therefore, f is isomorphism. F is isomorphism. Okay. So anyway, these are all conditions you have to check. Okay, so if it's both 1, 1 and onto under the homomorphism, then we say it's isomorphism. Now next definition, kernel of a homomorphism. Kernel. So this is very important. So kernel of a homomorphism. Suppose we have a homomorphism between two groups, then what is the kernel? Suppose if you take f is a function from some group G1 to another group G2, be a homomorphism. Homomorphism. Then we define the set kernel. Okay, so then we define kernel of f. We shortly write ker f. So this is nothing but we are collecting elements G in the domain which maps to identity element. That is, f of G should be identity element. So maybe we call E2 is the identity element in the codomain, E1 is the identity element in the domain. Okay. So for example, suppose this is our group G1 and this is a group G2. Since G1 is a group, therefore it has some identity element. We call E1 is the identity element of the group G1. Since G2 is also a group, therefore E2 is the identity element of this group. Now the kernel is nothing but is a subset of G1, which everything maps to this identity element. So we are collecting elements which are maps to that identity element E2. That set is called kernel of f, since f is a function from these groups. Okay. So this kernel, we can easily show that this is a subgroup of the domain. Okay. So clearly the identity element must maps to identity element. Okay. So that is f of E1. So E1 is the identity element of the domain. If f is a homomorphism, then this identity element so always map to the identity element of the codomain. That is f of E1 equal to f of E2. Okay. So first property. So therefore this set is a non-empty set. The kernel of f contains at least identity element. Okay, we can show that this kernel is a subgroup. So how to prove that the kernel is a subgroup? We take some arbitrary element a, b. Suppose I am taking two arbitrary element a comma b in the kernel of f. And what we have to prove? A b inverse belongs to kernel. Okay. So since a is in the kernel of f, by the definition of kernel, this a should map to the identity element E2. Since b also element of kernel, therefore this f of b also maps to the identity element of the codomain. Now what we have to prove? We have to prove that AB inverse belongs to kernel. That is, it is enough to prove that the f of AB inverse should be identity. So since f is a homomorphism, therefore this is nothing but f of A into f of B inverse. But we know that f of A is nothing but the identity element E2. And then f of B is nothing but we can write f of B whole inverse. Okay, I will prove now why f of B inverse is same as f of B whole inverse. Okay, so just to multiply f of B into f of B, inside f of b inverse. So this is nothing but, so f of, but since f is a homomorphism, right? So this is equal to f of b into f of b inverse. So this is nothing but f of b into b inverse, nothing but identity element. So this identity element in the domain, therefore E1. So therefore this is equal to f of identity element maps to identity element, therefore this is E2. So I multiplying these two elements, we get identity element. Therefore this is nothing but inverse of this element. Therefore this f of b inverse is nothing but inverse of this f of b. So therefore we can write f of b inverse nothing but f of b whole inverse. Again f of b equal to that identity. Therefore we get identity into identity inverse is nothing but identity. Therefore identity we get identity. So therefore f of ab inverse equal to identity. So from this part we can say ab inverse belongs to the kernel of f. So therefore kernel is a subgroup of domain. Kernel of any homomorphism is a subgroup now, but it's always normal subgroup. So it's a subgroup of the domain G1. So even more we can say that this kernel is a normal subgroup. So how to prove the kernel is a normal subgroup? We have to take some arbitrary element G in the domain G1, and then if you take some element A in the kernel, then what we have to prove? We have to prove G A G inverse belongs to kernel of F, right? So that is what we have to prove. F of G A G inverse should be maps to identity element. That is we have to prove. Okay, consider f of G A G inverse. Since f is a homomorphism, this is nothing but f of G into f of A into f of G inverse, but f of G inverse is nothing but f of G whole inverse. And since we are taking A is an element of the kernel, therefore f of A should be identity element. So therefore f of G into E2, E2 is the identity element of the codomain, and f of G inverse. So therefore we can cancel everything, we get identity element E2. Because f of G and f of G inverse is nothing but identity element, identity. So this G A G inverse maps to identity, therefore G A G inverse belongs to the kernel. Therefore kernel of F is a normal subgroup. Kernel of F is a normal subgroup. It's very important subgroup. Okay. Normal subgroup of the domain G1. Okay. So for any doubt? Okay, therefore given any homomorphism, we can talk about the kernel. Sometimes the kernel is, because kernel is a subgroup, therefore at least it contains 0 element. So there is an important theorem that, so if the kernel is singleton 0, so that means contains only 0 element, then the function should be 1 function. So note, it's very important thing. So kernel of a function, kernel of a homomorphism. So we define kernel only for homomorphism, not for function. Suppose the kernel contains only 0 element, if and only if the function should be 1 function. F is 1 to 1. If f is 1 to 1, the kernel is single digit. So we can prove this very simple proof. Okay, we have to prove this. Okay, anyway, you can keep in mind. So anyway, I will prove it. So maybe we can assume kernel is single, but 0 only maps to the identity element, and then you have to prove the f is 1 1. So how to prove f is 1 1? So assume kernel contains single 0. So kernel of f contains only 0. Now what we have to prove? We have to prove f is 1 1. So how to prove f is 1 1? Suppose we have to assume that f of x equal to f of y. Now we have to prove that x equal to y. Since we have to multiply f of y inverse both sides, therefore we get f of x into f of y whole inverse equal to f of y into f of inverse, we get identity element. Okay, that is E2 in the codomain. So since f is a homomorphism, we can rewrite this as f of xy inverse So here 0 means identity element, maybe you can take E1. Okay, so depending upon the group, if it is a additive group, the identity element is 0. If it is general group, we call E1. Okay, so this is equal to E1. So now what do you get? So this is equal to E2. Since this element xy inverse maps to E2, therefore this xy inverse should be in the kernel of F. But we know that the kernel contains only the trivial element E1, identity element. Therefore this xy inverse should be identity element. Now multiply y both sides, therefore x equal to y. Therefore if you assume kernel contains only identity element, the function is 1. Conversely, assume f is 1, 1 to prove that the kernel contains only the identity element. Suppose that if we take some arbitrary element, if we take arbitrary element x in the kernel, we have to prove that the x should be identity element. Okay, so therefore, suppose we take arbitrary element x in the kernel. By the definition of kernel, this x maps to identity element in the codomain, that is E2. And already we know that identity element also maps to identity element. The identity element of the domain E1 also maps to E2. Therefore, we get f of x equal to f of E1. Since f is 1, 1, therefore implies x should be equal to the identity element E1. Since f is, we assume that f is 1, 1. Therefore, we take arbitrary element in the kernel, we prove that that element is nothing but identity element. Therefore, the kernel contains only the trivial element, identity element E1. So, therefore, this result is very important. This is only for homomorphism. If f is a homomorphism between two groups, if the kernel contains singleton identity, then the function should be 1, 1 function. Okay. Now, so any homomorphism, now we produce one subgroup that is namely called kernel. Now, suppose we have again a homomorphism, f is a homomorphism, then we have another subgroup is nothing but the image of the set. Okay. Suppose f is a function from G1 to G2 is a homomorphism. A homomorphism. Then we are collecting, we use the notation f of G1 is nothing but range space. It is set of all f of G such that G in G1. So that is, this is our G1, this is our G2. We have a homomorphism between G1 and G2. We are collecting the only the image range. So this is f of G1. If it is onto this f of G1 equal to G2, if it is not onto, we will get some proper subset of G2. Okay. This is the image of the set. Okay. Even you can say that this is a subgroup of G2. So how to prove this is a subgroup of G2? Again, it takes some two arbitrary elements. Suppose we take two element A comma B in f of G1. Since A1, A comma B in A is in f of G, therefore A is of the form f of some G1. Since B is also in the element of image, therefore B is of the form f of some element. Maybe we can take G2. Now we have to consider AB inverse should be is of the form f of something. So what is f? A is nothing but f of G1 and f of G2 inverse. So we can take inverse inside. See, use the f is homomorphism. We get f of G1, G2 inverse. Therefore, AB inverse can be written as f of some element in the G2, G1. Therefore, this AB inverse belongs to the image of the set. Therefore, this image of the set is a subgroup. So, but in general, that is not a normal subgroup. Okay, you try to prove it. Okay, anyway, now given any homomorphism, we have two subgroup. One subgroup we produce in the domain, that is kernel. We produce kernel is a subgroup in the domain. We produce one more subgroup in the codomain, that is image of the set. Okay. Now we have a theorem, that is fundamental theorem of, or first, not fundamental, it's a first homomorphism theorem. So that is theorem is called, okay, first isomorphism theorem on groups, or fundamental theorem of homomorphism, first isomorphism. So fundamental theorem of first, otherwise first fundamental theorem. First fundamental theorem. Right, first in the first. So first fundamental theorem of isomorphism. Isomorphism is group isomorphism. Okay. So simply says, suppose we have a homomorphism from one group G1 to G2. Be a homomorphism. If any homomorphism, then the theorem says G1 by the kernel of F, the quotient group. Because since kernel F is a normal subgroup, therefore we can talk about the quotient group. And this should be isomorphic to the F of G1. Okay, not G2, F of G1. So G1 by kernel is isomorphic to F of G1. It's very, very important theorem. Okay. Now, based using this theorem, we have some problem. So now, okay. Second, there are another theorems are there. A second fundamental theorem, and then another one is third fundamental theorem. So this is the first fundamental. Second fundamental theorem, I think says we directly write the formula. So order of H intersection K, sorry, order of H into K. So again, okay, we have some result which we have to we have to discuss. Okay, maybe I can write here. The results are, so product of two subgroups need not be subgroup. Okay, again, union of two subgroup need not be subgroup, but intersection of two subgroup is a subgroup. So maybe I can write here, union of two subgroups need not be subgroup. Need not be a subgroup. So when union of two subgroup is subgroup, one subgroup is contained in other subgroup. Okay. So maybe you can write the statement, union of two subgroup is subgroup. Union of two subgroups is a subgroup only when one is contained in other. Either if you take H and K two subgroup, H union K is a subgroup. Either H is contained in K or K is a subset of K. So only when one is contained in other. Otherwise, union is need not be a subgroup. Now the intersection of two subgroup is always subgroup. Intersection of two subgroups is always subgroup. Now the product of two subgroup is a subgroup only when, so therefore if you take two subgroup H and K, so H into K, the product is a subgroup if and only if that satisfies the property HK equal to KH. So what do you mean by HK? H is a one subgroup, K is another subgroup. So HK is nothing but product of the element is of the form H into K, where H varies in H, K varies in K. Okay, if HK equal to KH, then HK is a subgroup. Okay, otherwise the product of two subgroup need not be a subgroup. So this is very important result. Now the second fundamental theorem based on the order of the subgroup of the subgroup product. So maybe I can write here, This is a fundamental second fundamental theorem of a ice group homomorphism. There is order of the product subgroup is nothing but order of H into order of K by order of H intersection K, where H and K are subgroups. Or even we can say in the isomorphism. So once you know the formula, we can easily write the thing. So what is that? HK by K is isomorphic to H by H intersection K. Okay, this is the simple thing. Where K is a normal subgroup of HK, H intersection K is a normal subgroup of H. So whenever we define the quotient, the denominator should be a normal subgroup of the numerator subgroup. Okay. So otherwise, you just remember this formula. So order of Hk equal to order of H into order of K by order of H intersection K, where H and K are subgroups of the group G. So both H and K are subgroup of G. So whenever I use the notation less than or equal to means subgroup. Okay, H is a subgroup of G, K is also subgroup of G. So whenever this is a notation is less than or here, but whenever we usually use the containment, but suppose some books are used less than or equal to denote these subgroups. For denoting the normal subgroup, they use the delta and then as equal. So this means H is a normal subgroup of G. Okay, so don't confuse the notation. Sometimes they use the just H less than or equal to G. That means what? H is a subgroup of G. If H delta G means what? H is a normal subgroup of G. Okay. Now this formula is very important. This is say second fundamental theorem of group homomorphism. The third fundamental theorem says, okay, suppose we have two groups H, and this is subgroup of another subgroup K, and this is subgroup of G. G is a group, H is a normal subgroup of K, K is a normal subgroup of G, then G by K by K by H is isomorphic to K cancel, we get G by H, like this. Because K is a normal subgroup of, so maybe I can write here. So this is a normal subgroup of these, and this H is a normal subgroup of these. Now the quotient we can define G by H. This group divided by this K by H is isomorphic to G by H. This is the third fundamental theorem of isomorph groups. Now maybe why you can say here, if you take suppose H is a normal subgroup. Okay, H is a normal subgroup of G, then we define the quotient group, right? G by H we can define. So whenever H is a normal subgroup, then this quotient is a group. Now in that group, how the subgroup look like? Okay, suppose if you take some L is a subset of G by H is a subgroup. Is a subgroup, then this L is of the form K by H, where K is a subgroup of, here the denominator is fixed, okay, where K is a subgroup of G. Again, if you take any normal subgroup in the quotient group, is of the form K by H, where K is a normal subgroup. Okay. So in the group, the quotient group G by H, the identity element is H. So the denominator is the identity element. So in the group G by H, H is the identity element. Identity element in the group. Identity element or zero element in the group. So whenever they define the quotient group, the denominator subgroup is the identity element. Okay, and any subgroup of the form K by H, where K is a subgroup of G, and any normal subgroup of G by H is of the form K by H, where K is a normal subgroup. So that's why I am writing this K by H. So whenever we define the quotient, here I am defining the quotient. Therefore, this K by H, I think I did some mistake. I think this is H, this is K. Okay, therefore this K by H is an normal subgroup of G by H. So we get G by K. Okay, so just rewrite this. G by H by K by H is nothing but G by K. This is the third isomorphism theorem. So therefore any subgroup in the quotient groups of the form K by H, where H is fixed. Keep in mind. Now there is a important problem. So exercise. We know the integer modulo n group is Zn. Suppose I am defining a function here from set of all integers to the integer modulo n Zn. Okay. How we define the function? F of any x, I am taking x modulo n. Modulo n. So we take only the remainder when it is divisible by n. So for example, if we take better we take instead of taking n, and suppose taking some 5. So what is the function? F of x equals to x modulo 5. So for example, what is f of 10 is nothing but 0. 10 maps to 0. So what is f of 7? If you remove all the multiples of 5, we get 2. Therefore f of 7 maps to 2. What is f of minus 8? Again, this is multiples of this is nothing but 2. Why is 2? We know that 10 is congruent to 0 modulo 5. This 10 can be written as 8 plus 2. 8 plus 2 is congruent to 0. Now take this 8 beside, therefore 2 is congruent to minus 8 modulo 10. Therefore, whenever we have a negative term, negative number, we can convert it to positive number. Therefore, this minus 8 maps to 2. So these are the function. Now we can easily show that this is a homomorphism. Okay, F is homomorphism. Now, what are the elements? What is the kernel? So whenever we define the homomorphism, we can talk about the kernel. So what is the kernel of the homomorphism? By the definition, we are collecting the integer such that the f of x should be 0 modulo 5. So we take so f of x nothing but just x. So we are collecting the integers, satisfy the condition x is congruent to 0 modulo 5. So that means what? If we take modulo 5, it should be 0. Therefore, x should be multiples of 5. Therefore, x should be multiples of 5. Therefore, we can write 5 times z. So 5 is nothing but all multiples of 5. Therefore, by fundamental theorem of first isomorphism theorem, z by kernel, here kernel is 5z, is isomorph by 2 range. The range always contains z5. This maps all the elements. It's onto function. This is in general. Okay, in general, it's a very important result. In general, z by the n z, all multiples of n, is isomorphic to z suffix n. Very, very, very important result. So z by n z is isomorphic to zn. Okay. So anyway, so we can stop now. Thank you.